All right, let's dive right in. We're about to pull back the curtain on something you use every single day, but maybe don't fully understand. We are going on the invisible journey your data takes every second to see how the internet actually works. So, buckle up, the trip starts now. It all begins with something so simple, right? A single click. You probably do it thousands of times a day without a second thought. But that one tiny action, man, it kicks off this incredible high-speed trip across the entire globe. We see it as instantaneous, but the process behind it is an absolute masterpiece of engineering. So to really wrap our heads around this, we're going to use an analogy that everybody gets, the good old postal service. Just think of your request to watch a video, load a web page, whatever, as a letter you need to send. We're going to follow that letter from your digital house all the way to its destination and back again. Okay, first things first. Before our digital letter can go anywhere, it needs to be packaged and addressed correctly. This first step, preparing the data for its big trip, is what makes the whole rest of the journey even possible. Here's the thing. A big message, like a really high-def photo, can't just be sent all at once. It's too clunky. Instead, your computer is smart. It chops it up into these tiny, super efficient pieces called packets. Now, sending a long letter as a bunch of separate postcards might sound kind of weird, but it's the secret sauce that makes the internet so fast and so reliable. This whole process has a name, encapsulation, and it's like an assembly line. Each layer of software adds its own header. Think of it like this. One layer writes the recipient's address, another adds the return address, and another one puts instructions on how to piece all those postcards back together in the right order when they arrive. Finally, these fully addressed packets get dropped into the digital mailbag, ready to fly. All right, our digital letter is all packaged up. It's ready. Now for the very first leg of its journey, just getting out of the house. And this all happens on what's called a local area network. A LAN, or local area network, connects all of your nearby devices. Your laptop, your phone, the smart TV, your printer, all of it. It's your own private little network that handles all the digital traffic inside your own four walls before it ever even thinks about touching the public internet. On this little local network, your devices are talking to each other constantly. It's like a nonstop dance of requests and replies. Your laptop acts as a client when it asks for a web page. And in an office, that shared printer, well, it acts as a server by providing a printing service. And your Wi-Fi router, it's the director of this whole local dance, making sure every request gets to the right partner. Now, these local networks can be physically set up in different ways, and these layouts are called topologies. Way back when, you might have seen a bus layout, where everything was hooked up to one main cable. Or maybe a ring, where data was passed around in a circle. But today, one particular layout is king. You got it. It's the star topology. All of your devices, every single one, connects directly to a central hub, which is your Wi-Fi router. It's simple, it's easy to manage, and it's why it's the undisputed champ for home and small office networks. Of course, it also means that if that router goes down, your whole network goes down with it. And just like that, our packet has successfully left the building. Now it hits the open road. It's entering the wild, vast, and totally interconnected world of the wide area network. The WAN is what most of us just call the internet. It's this massive, sprawling network of networks that connects cities, countries, and whole continents. So going back to our analogy, our little packet is no longer in a private mailroom. Oh no, it's now in the hands of the full-blown global postal system. So the backbone of this WAN is built on two absolutely critical parts. First, you've got the transmission lines. These are the physical highways. We're talking undersea fiber optic cables, copper wires, radio links that actually carry the data. And second, you have the routers. These are the super smart sorting offices. They read the address on each and every packet and then forward it to the next router on the best possible path to its final destination. It's incredible. What's really interesting is that you can see the trade-offs as a network gets bigger. Inside your house, on your LAN, everything is blazing fast with very little congestion. But as you expand out to a citywide network, a MAN, and then to the global WAN, the potential for digital traffic jams just skyrockets. And that is exactly why those smart router sorting offices are so vital. They are literally the traffic hops for the entire internet. Okay, hold on. We've got billions of devices, right? Made by thousands of different companies, connected by all these different kinds of cables and wireless signals. How on earth does it all actually work together? How does everything speak the same language? Well, the magic ingredient, the secret that makes it all possible is protocols. A protocol is really just an agreement. It's a shared set of rules for how to communicate. It's like a universal translator that makes sure a device in South Korea can perfectly understand a packet that was sent from a server in Brazil. To keep all these rules organized, engineers came up with a couple of frameworks. First, there's the OSI model. It's this beautiful 7-layer, perfect theoretical blueprint of how a network should work. But here's the thing. The internet wasn't built in a lab. It was built by pragmatists. They just used what actually worked. And that led to the simpler, messier TCP/IP model. It's a classic story of messy reality winning out over perfect theory, and it's the standard that runs our internet today. And really, it all just boils down to this entire mind-bogglingly complex global network. It functions because of a simple, incredibly powerful idea: agreement. This shared rulebook is the true foundation of our connected world. So now that we've followed our little pocket on its epic journey, let's zoom out one last time. Let's look at the unbelievable system we've all built and some of the really big questions it raises for our future. I mean, just think about it. This global network has woven itself into the very fabric of modern life. It's completely changed how businesses operate, how we shop and get information from home, and of course, how we stay connected absolutely anywhere, anytime, through our mobile devices. And the pace of all this innovation is just staggering. Seriously, it really wasn't that long ago that we were getting excited about speeds of a few thousand bits per second. Today, a standard wired connection in an office can hit 10 gigabits per second. What does that even mean? Well, that's fast enough to download a full, high-definition movie in about 4 seconds. It is 10 billion bits of information flying down a single cable every single second. That is the kind of speed our modern world is built on. But of course, this amazing connectivity creates brand new, really complicated challenges. Every one of these issues is a fundamental tug of war. The government's need for security versus a citizen's right to privacy. An employer's desire to monitor productivity versus an employee's rights. A creator's right to get paid for their work versus the sheer ease of digital copying. In a world without borders, whose laws even apply? These are the tough questions we now have to figure out as a global society. So, we've built this invisible, planet-spanning machine that now holds up our economy, our relationships, our entire society. And that leaves us with maybe the most important question of all. Who gets to write the rules for its future? Should it be the engineers who build it, the governments who try to regulate it, the corporations who profit from it, or should it be all of us? Thanks for joining this explainer.